Welcome to my channel. I'm Zhang Jingxu. Let's look at the problem 30 in chapter 30. Chapter 30 is about inductance, electromagnetic oscillations, and AC circuit. You can see now we have two solenoids with the same length and the circular cross-sectional areas. But the first solenoid, so solenoid 1 uses wire that is 1.5 times as thick as the second one, right? So now first one asks you the ratio of their inductance. For solenoid, we can see the inductance we can write in this equation. And in this equation, you can see mu naught is a constant. A is the cross-sectional area. It tells you these two equals. And L is the length of these two solenoids equals, right? So looks like only variable is N. How many turns of these solenoids? And then we can see we know the thickness, so that is diameter for the wires for the 1 over the diameters of the 2 equal to 1.5 from this sentence. Agree? Yes. Now, how can you convert the ratio from the D to the N? So we can say we know these two solenoids are same length. What means the same length? For this solenoid, how can you calculate its length? From this side to this side, agree? And you can see for each turn, the length is just the diameter D, right? And this D times the how many turns N equal to this length, agree? So for the solenoid 1, the length is N1 times D1. And for solenoid 2, the length is N2 times D2, right? These two should equal. It tells us these two solenoids same length. So in this case, we can write down the N2 over N1 equal to D1 over D2 equals 1.5. Now, it's problem solved. We write down the equations for the inductance there. So the ratio L2 over L1, we just input the term for L2, the term for L1. You can see mu naught A and L cancels. So we get is N2 squared divided by N1 squared. There, we know the ratio N2 over N1 is 1.5. So this becomes 1.5 squared. So we get answer there. The second one tells us what is a ratio of the inductive times constant? Now, time constant. So as we learned in this chapter, time constant is L over R, right? This is the inductance over resistance. But luckily, we know the ratio for the inductance from part A. That is there L2 over L1 is 1.5 squared. Now looks like we must find the ratio for the resistance. As we learned in previous chapters from Ohm's law, resistance can be written as rho, the length of the wire divided by cross-sectional of the wire, right? And this one can be written as pi r squared, pi times radius squared, so this is d over 2, right? Since it looks like we need to find the ratio for the wires. And now, how can you, for this solenoid, how can we calculate its wires? So we can see this one, it becomes easy, right? Because it makes 1 turn, 2 turn, and 3 turn. And then this D, we can consider this is D. For 1 turn, what is the length for the wire? Pi times D, right? And for the wire 1, how many turns it has? N1. So this is the length for the wire in first solenoid, right? And the wire length for the second one, so this is N2 times pi D. So pi D can cancel, so we have N1 over N2, so we get it there, 1 over 1.5. Now everything is prepared. We can write down the R1 over R2, the ratio, input this first term and the second term, and we can say rho and pi cancels, so we get it look like this one. And then input the ratio of the wire length and the diameters ratio squared, we get it there. Now things becomes much more easy. look at the inductive time constant ratio, tau 1 over tau 2. So we can write tau 1 as L1 over R1, tau 2 as L2 over R2. And just simplify it, looks like this one. And there you can see we have the ratio for the L2 over L1, and we also have the ratio for R1 over R2. You input these two inside, you get answer there.